Okay, so we're going to take a look at simple harmonic motion, and the first question is, well, what the hell is that? So I'm just going to draw this pendulum point with a dotted line which just represents straight down from the point. And then we might have a little ball attached on a string, and it's going to be accelerating in towards the middle, okay? And then from this origin point, this is our displacement x, okay, and you notice that the acceleration and the displacement go in opposite directions, and if you think about it, this acceleration is going to be proportional to this displacement, okay, but in the opposite direction. So the differential equation that's going to solve this is some sort of differential equation where the second derivative is equal to some minus ax, where a is greater than 0. Well, how do we write this down? Well, we tend to say that d2x dt squared is equal to minus omega squared x, and that's because omega squared, omega is real, so omega squared is going to be positive, so that takes care of that. And then it turns out this omega has some nice properties in the solution. Okay, it makes the work a little bit neater than writing some a or whatever, or and then having square roots in our solution. So if we look to solve this, we need to think of a function that's when it's differentiated twice is proportional to minus some constant. And it turns out the general solution, if you think about it for a second, I'm sure you can get this, is x is equal to a sine omega t plus b cos omega t. And how do we know there's no more solutions? Well, for a second order equation, we need to look for two linearly independent solutions. And once we have that, we know any linear combination of that makes up the whole solution set. Okay, so we can make up the whole solution set with linear combinations of sine omega t and cos omega t. So a and b are just constants. Okay, and so that's the general solution. If we were to find the actual solution for a specific setup, and another harmonic, simple harmonic motion thing might be a spring. Okay, that's just sort of like oscillating back and forward. Then we need initial conditions. So we might say, is the pendulum starting straight down with a push so that it's getting some acceleration? Okay, we're just starting in the middle, or are we holding it up still here and then just letting it form? All sorts of stuff like that. And that will give us our initial value for x, okay? And we can also have some initial condition on the velocity, which is dx by dt, which we can use to. The last thing I want to check in this video is that this is actually a solution. So let's differentiate it. So dx by dt is equal to a omega cos omega t minus b omega sine omega t, and then d2x by dt squared is equal to, now we get the negative here, so we get minus a omega squared sine omega t minus b omega squared cos omega t, taking out the minus omega squared, then we get a sine omega t plus b cos omega t, and of course this here is x, so that's what we wanted. So yeah, that's simple harmonic motion, and notice simple harmonic motion is the case when this will swing all the way to a symmetrical point on the other side and then come all the way back to the same point. So there's no friction or resistance forces, there's no loss of energy in the system. Okay, and this can be a useful model, but sometimes we need to look at something called damped harmonic motion, and we'll look at that next, and that'll be our last sort of video in the pure mathematical syllabus. Another question you might have is, why is this in the further maths pure syllabus? I have absolutely no idea. Should really be in mechanics, but I guess they just fit in as part of the differential equations because it's a nice example of a differential equation. But anyway, thank you for watching this video. I hope to see you in the next one.